Hello there, I'm Thomas Hatsios, the British American pilot flying the Boeing 777-300 ERA. Tonight's flight from Zurich International Airport. We're going to be overflying Zurich, Switzerland, Germany, and then coming back to the Zurich International Airport. Uh, Runway 14 for an Lszh localizer landing. So right now I'm in the cockpit for the pre-takeoff preparation of the Boeing 777-300 ERX of the PNC simulation and Microsoft Flight Simulator X. So I'm going to start showing you the cockpit instruments, the displays, um, uh, and the panel of the Boeing and also the functions of the Boeing 777-300 ER airliner aircraft. So I'm gonna start with the primary flight display. The displays the airspeed indicated, the ground speed, the airspeed selected from the autopilot and flight director system panel, the radio altitude above the ground level, the magnetic heading and track, the magnetic north pole and the true north pole, and the magnetic variation depending on where we are in the world. We have also the altitude indicator with the pitch ladder in degrees and the bank angle in degrees. We have the Lszh localizer and the flight director crossbars for manual guidance of the aircraft. Also we have the autopilot crossbars for automatic guidance of the aircraft. We have the angle of attack of the aircraft. We have the radio altitude above the ground level, the barometric altitude above the sea level, and the barometric pressure of the outside atmosphere. We have the target altitude selected from the autopilot and flight director system panel, the flight mode annunciator with the autopilot and auto throttle later on vertical navigation modes, and also the VSI tape, the vertical speed indicator that displays the vertical rate of climb or descent of the aircraft in tens, hundreds and thousands of feet per minute. So we have also the navigation display. The navigation display that displays the airport, the waypoints, the nav aids, the GPS position of the aircraft, inertial reference position. We have the RMP and the ANP, the required navigation performance and the acquired navigation performance. We have again the magnetic north pole and the true north pole and magnetic variation depending on where we are in the world. We have the terrain, the weather radar and the terrain reflections from the weather radar displayed as red, green and yellow elevation levels, and the distance range in nautical miles like 160 or 320 nautical miles of distance covered from the weather and terrain map radar. So we have also other aircraft displayed from the ADS-B and ADS-C transponder, which acts as a passive radar and transmits our own position, altitude, and airspeed, and also receives from the other aircraft flying around us. And so they display using the TICA system, the traffic collision and alert system that generates traffic collision alert advisories. So we have also the flight management computer. We're gonna use it to input the data of the aircraft, like the takeoff weight, the fuel on board, the passengers and the cargo on board, and the runway we're gonna use for takeoff in this specific airport, the runway length, the elevation above the sea level, the wind direction and airspeed, and also the barometric pressure and the temperature of the air. And so we're gonna generate the takeoff speeds, and we're gonna generate a flight plan, a horizontal and vertical flight path for automatic or manual guidance of the aircraft. So I will explain you all these things later. We're gonna use after selecting the departure airport and runway. We're gonna use the seats, the stagger instrument departure, the intermediate waypoints for the vertical and lateral navigation, and also the destination airport and runway. We're gonna make a complete route for the aircraft that can be followed using the autopilot, or can be followed manually with the destination starter terminal arrival, and also the Lszh localizer of the runway of the destination airport. Uh, so you're gonna see that. Also I'm gonna show you then the autopilot and flight director system panel, the FTS, that contains the autopilot engage and disengage switch, the auto throttle left and auto throttle right engage and disengage switch, the flight director engage and disengage switch. We have the flight level change, the airspeed select knob. We can select the airspeed in nautical miles per hour or Mach speed, and select the modes like the flight level change, the auto throttle with the speed mode, and the climb continuous mode. So we have a couple of modes of navigation for the speed guidance of the aircraft, which commands the auto throttle system, and the FAREX. The FAREX are the fuel authority, these electronic control computers that control and monitor the engine's functions. So we have the fixed thrust mode for climb and takeoff, and also for idle thrust for descent. And we have the variable thrust mode like the cruise and the operation lighting. So we have in the fixed thrust mode the thrust is being maintained fixed constantly, and the airspeed is being adjusted by varying the rate of climb or descent of the aircraft using the horizontal elevator trim signal in the elevator of the aircraft. So the horizontal tail of the aircraft. So then I'm gonna show you. I told you we're gonna see the FADEX, the full electronic control computers. One is the per engine. I'm gonna come later to that. I'm gonna show you then in the autopilot flight director system panel, the LNAV and the VNAV. We have the lateral navigation and vertical navigation of the aircraft. I'm gonna show you also we have the bank angle limit and the heading select node. We have the heading hold switch, and we have the flight path angle of the aircraft and the VS vertical speed rate and the selected mode using the slider with which we can adjust the trigonometric angle in degrees for the climb or the descent of the aircraft from a horizontal flight path like the cruise level or in a climb. So also we can select a rate of climb or descent in tens, hundreds, and thousands of feet per minute. And this is displayed in the vertical speed indicator or the flight director crossbar. Then I'm going to show you the altitude select knob and the altitude hold switch, and also the VOR localizer for the Lszh localizer approach, and the approach switch for the auto function of the Boeing 777-300ER airplane. So I'm going to come now. You can see here the displays of the aircraft and the instruments inside the cockpit. We're gonna use like the flight controls, yoke, the control column, and the control wheel, and also the rudder pedals. We have the nose wheel steering over there. So I'm gonna come later, talk to you about the autopilot, and I'm gonna come to the thrust levers. So using the thrust levers, I will explain you the function of the engine thrust levers, how you can use them to adjust the thrust manually using the thrust lever angle position, or you can use the autopilot and flight director system with the auto throttle and the auto thrust system. Also the flight management computer mode, which is interconnected to the LNAV and the VNAV navigation of the autopilot and flight director system panel. I will show you how you can use the auto throttle disconnect switch and the thrust reverse, other things like we have the General Electric 90 G90 engines, turbofan jet engines installed in our Boeing 777-300ER, one in the left wing and one in the right wing for symmetrical thrust and redundancy, which produce a lot of thrust because it's a turbine engine, a turbojet. So I'm gonna show you also, after that I will explain about the flight wheel of the aircraft. I will show you the flight controls as I told you, explain you how to calculate the takeoff speeds, then I'm gonna show you the overhead panel after showing you all the flight controls here. I'm gonna show you the overhead panel over here, all the systems. As you can see, we have the electrical, the IDVs, the integrated drive generators, which are interconnected to the engines. They produce alternate current 400 Hz, 130, 200 volts, 130,000 kilovolts or 130,000 watts. of alternate current, also the backup generators 35,000 kilovolts, and the APU, the auxiliary power unit, another 135,000 kilovolts. We use the APU, the auxiliary power unit, for starting the engine in the ground or as a backup in the flight. Also, I'm gonna show you the batteries, 38 volts, 48 amp hours. I'm gonna show you the primary flight control computers, the ADIRO, the Advanced reference unit. I will explain its function. I will show you also the hydraulic pumps, the left engine and right engine, and the electrical C1 and C2, the pressurized hydraulic pumps also, and tanks. I will talk to you about how we use them for the flight controls function, about the landing gear, external thrust, and also the parking brake and other systems, like the thrust reversers. And uh, I will come then to the electronic engine control of the engines, the auto start system, the cabin pressurization system of the aircraft, the bleeder from the left and the right engine. I'm gonna show you also the fuel tank, the left wing and the right wing tank, the fuel they contain, and also the forward and the aft pumps, the fuel system of the aircraft, the fuel control computers, and the fuel valves to the left and the right engine, the low and high pressure fuel valves, and the startup valves for this. I'm gonna show you then. I will show you and talk to you about the cabin pressurization system of the aircraft and the bleeder from the left and the right engine. We need for cabin pressurization, wing and engine ABIs, air conditioning and ventilation, and also for the hydraulic fluid pressurization of the C1 and C2 systems. So I will show you all these things. Also the flight controls, I told you the ailerons, the spoilers in the left and right wing, the horizontal tail, the elevator and the trim, and also the vertical stabilizer, the rudder, and also the horizontal trim stabilizer function, and the rudder trim function for horizontal stabilizer total city. So I will show you and explain all these things, and I will make a flight plan using a flight management computer and show you an auto start for the engine. And then I make a small flight using the Boeing 777-300ER. So thank you very much one more time for joining me, and most happy the British American Power flying the Boeing 777-300ER flight. So I'm gonna start now, showing you inside the aircraft and the whereabouts, and also the outside view. So you can see here we have the main panels and the displays of the Boeing 777, also the outside view of the aircraft. So we have about an hour left for this flight. So hope you like it. You can see also the airport we are located here. So you can see here we have the primary flight display. That displays the airspeed indicated, the airspeed selected, the ground speed, the barometric altitude above the sea level, also the barometric pressure above the sea level, the radio altitude above the ground level, the magnetic north pole and true north pole, and also here in the navigation display we can change this from magnetic to geographic north pole. So we can set also the meters here and the hectopascals for the barometric pressure. So we have 1013 hectopascals and 30,050 meters for the climb rate. So I will have to show you now. Also we have here we can set here the auto throttle left, as you can see, and the auto throttle right off. You will see either one displayed as auto throttle left and auto throttle right over here. is off and only the other one is on. So we set again. We can also set here is the flight director on and off the other side, so we can set the flight level change like this. Select an indicator airspeed or Mach like 253 for after takeoff. This is also depressible. We have the LNAV, the VNAV, the climb continues, you go to throttle, the bank angle limit for the flight level. Also you can deselect this, you depress this switch. So we select the heading of the runway for takeoff like 136 degrees, heading track again, indicated airspeed Mach. So you can see here also we have the vertical speed, flight path angle, and the altitude hold. So we can set the altitude here like 35,000, and this is also depressible. As you can see, this is the autopilot disengage. So you will see now different values over here. We have the flight level change again, 35,000 over here. Flight level change speed, flight director 25,300, 1013 hectopascals. So we may set a couple more values, 253 nautical miles per hour the airspeed. You can set the autopilot like this on, this off, and back on again, and you see both sides. Also you see the autopilot here is on, flight level change, heading hold, this altitude 35,300, and this airspeed, the flight director of the crossbar, you can see the pitch ladder 2.5, 5, 7.5, 10 degrees, 12.5, 15, 17.5, 2 degrees, 1,430 feet or 436 meters. And the heading again, we set the heading and the barometric pressure 2 inches of mercury. We have again the magnetic north or true like this. So this is the geographic north pole instead of the magnetic. You need to use the other one. So we have also the altitude hold like this. You will see the altitude mode over here for the target altitude, and the heading hold with this airspeed. So a couple more modes. We have the vertical speed, as I told you, the flight path angle. So if you set a negative like minus 3.1 degrees for descent, you will see the descent rate here. If you select from the cruise level, you will see pitch ladder tick markers over here in between the 0 and the minus 3.1. So we select a positive, like for a climb. You will see the other way. We're gonna move the slider. So moving the slider this way, up or down, changes the indicated value, northwest for climb to 3.9 degrees now. Over here, and you see the pitch ladder. This is gonna guide the autopilot, the flight director guidance. So we can use the vertical speed in tens, hundreds, and thousands of feet per minute like this. Set a minus, like minus 2,700 feet per minute. You will see the minus over here. minus 2700. You can set the plus. So this is gonna request a climb from the autopilot. In flight director system panel, you can see 253 again, nautical miles per hour, vertical speed, heading, hold, the target altitude and target heading. So this target altitude could be 5,300 feet or 7,710 meters. So I'm gonna show you now other indications and values. I can show you how to disengage. If you press this out, you will see again one more time. Press this out and you have the warning over here and also the autopilot disconnect. You can see with the red light, autopilot disconnected. Again engage. Press this switch and it disconnects again the autopilot. You can see again the autopilot, the warning, and now the autopilot disconnect. This is for the control wheel of the aircraft. So you press one more time and you confirm the disconnection and it cancels the warning. So we can continue like this. I'll talk to you now about the thrust lever. Before that, I will show you here we have these indications. You can see if we have flight instruments, hydraulics, electrical, engine, CPU, we have a failure. What we need to do, the flight controls, if we have a failure, for instance, in the stabilizer. So this is how you can see that in the non-normal. The stabilizer is red again. The normal menu. So this is the normal. If we have a failure, the electrical also. Flight instruments and displays, the reset, and the normal menu. So I will come later to that. We have the engines now here display. So I will talk to you now about the thrust levers. What you can do using all the thrust levers. And we have about 30 minutes left for this for you going to take off. You can see here again on the view. Hope you like it. So the thrust levers, you can see if we have the thrust levers at idle and the speed brakes extended. If we move the thrust levers forward, the speed brakes retracts automatically. So we have also the flaps over here, up and down. You can see the flaps, the position, the target over here, the landing gear up and down, some instruments, the alternate gear, the terrain override over here, the auto brakes. You can see the trademark of the aircraft, You can see also some messages. You can see the duct pressure, the leader pressure from the left and the right engine, the total fuel on board in thousands of pounds in the left and the right wing, the center tank assembly. So we have the indications of the engines here. I'm gonna start explaining you. So we have the N1, which is the low speed starter and shaft, and the low pressure compressor and turbine of the turbofan turbojet engine. We have the exhaust gas temperature per engine, the left and the right engine also, the bleed air from the left and the right engine. The N2, which is the high speed starter and shaft, the high pressure compressor and turbine of the turbofan turbojet engine, the fuel flow per engine per hour in thousands of kilograms or in thousands of pounds, the oil pressure or temperature or quantity and the vibration of the N2 stage of the engine. Here you can see the thrust levers. If I move forward, you will see the limits here. The thrust levers moving forward or down, you will see the difference between the requested and the actual thrust. It takes some time for the engine to spool up or spool down. You can see the limit 104.6% of the rotation speed for maximum continuous thrust or takeoff burn. I will show you now and talk to you about the thrust levers. Also, you can see the thrust levers. We have a couple of stuff like we have two thrust levers. You can use either one at a time, so you can have asymmetrical thrust like this. Differential thrust. So you see over here, one engine is forward, it has more power, the right engine and the left, and set the bolts together, and then again. You can use asymmetric thrust, like more thrust in the left. As you can see, you can set the bolts together. We have the takeoff go around switch over here. We have the auto throttle disconnect over here. You press this one time and you disconnect. The auto throttle, we have the thrust reverse. So if the speed brakes are extended, then you push the thrust reverse as the speed brakes deploys automatically. So we have here, you can see the thrust reverses are open, the exhaust gas temperature. So here we have the thrust reverse for both engines, the left wing and the right wing, as you can see. So we cancel this, you can see the thrust reversal. Retract, also extend again. Again, retract like this. And extend one more time like this. So you have the thrust reverse being deployed. So you need the thrust reversers to slow down the aircraft after landing or in a rejected takeoff. If you are in the runway for takeoff or for landing, so just after touchdown. So I will talk to you now about the thrust levers. As you say, we have the general electric 90 installed in the left and the right wing to the front of the engines that produce all the thrust. So we use the thrust levers to adjust the thrust manually to give a signal to the paddocks. The paddocks are full of rated and cranked for continuous one installed per engine, left and the right engine, dual channel rebalancing, one channel stays, the other takes over. The display monitor all the indications and the parameters we see in the upper and the lower ACAS and the indication to our left system display, like the N1, which is the low speed starter and shaft compressor and turbine of the turbofan turbojet engine, the exhaust gas temperature per engine. The N2, which is the high speed starter and shaft, the high pressure compressor and turbine of the turbofan turbojet engine, the oil pressure, oil quality, oil temperature, the fuel flow per empty per hour in thousands of kilograms or in thousands of pounds, and the vibration of the N2 stage of the engine. We also actually can monitor other things like the engine start, engine shut down, the fuel flow rate, and the fuel mixer, also the pressure inside the engine. If we have an lower pressure, we allow the outflow valve to assist in the ninth stage of the blade into a higher setting, so they relieve the pressure from the mount inside the engine. If we have an under pressure, they close it into a lower stage, so they increase the pressure inside the engine. So this aircraft also has a price from lower and higher altitude. We have variation of the barometric pressure and the density of the air atmosphere, and also the temperature is becoming freezing at the cruising level about 20,000, 30,000, 40,000 feet. We have half of the barometric pressure and half the atmospheric density, air density that we have in sea level. So also the aircraft flies with a higher airspeed rate, like 2 or 3 times that of sea level. So we have different fuel mixture requests every second. So this is done automatically by the Flught. We don't have to do this manually. Also, when we descend to lower levels, we have again different fuel mixture requests. So it's a good thing to have the Flught. We also monitor and control the engine side, engine side down, engine side up. So this is a few things you can use the Flught for. And then I'm gonna talk to you about other things like the autoflow and the autothrust and the modes we're using the connected with the manual thrust setting. So I will talk to you now about the flight theory of the aircraft. I will show you how we can calculate the takeoff speed. So for this aircraft, the Boeing 777-300ER right now, we have 254,000 kilograms of takeoff weight, or 531,000 pounds, which is below the maximum takeoff weight. We have about 104,000 pounds of fuel on board, or 46,000 kilograms, which is only 30% of the total we can take. We have also about 30,000 kilograms of passenger cargo, 46,000 pounds. So in total we have 254,000 kilograms, or 531,000 pounds, which is below the maximum takeoff weight we need for this runway. Length, elevation above the sea level, barometric pressure and density, and also temperature of the air and wind direction and magnitude. We need to calculate the takeoff speed, also the conditions of the runway, if it is wet, dry or ice, and we need about 15 degrees of flaps and 4 degrees of horizontal tail trim stabilizer for takeoff. We need to overcome the stall speed of the aircraft and achieve an airspeed of about 154 nautical miles per hour, 154 knots, or 270 kilometers per hour just for takeoff. To overcome the stall speed, the stall speed is going to make the wings of the aircraft not produce the necessary lift force using the airflow that surrounds the wings during the takeoff phase and the flight phase. So the airstream around the wings generates the lift force that overcomes the weight of the aircraft that is equal to the mass times the acceleration of the Earth's gravity, depending on where we are in the world. Also, the thrust of propulsion from the engines overcomes the static and the kinetic friction into the aircraft body. So we have about 32 more minutes left for that, so I will talk to you now about the newtons per second law of kinematics. I will show you the outside view of the aircraft and talk to you about the flight theory of the aircraft, about aeronautical and aerospace engineering, about the new theory of fluids and physics and mathematics. So I will talk to you about this. I will show you now. So you can see here we have you can see how symmetrical the aircraft is. You can see the aircraft weight has been divided over the surface area of the wings. You can see we have the left and the right engine propulsion that moves the aircraft forward. You can see we have this lateral axis from the wingtip to the wingtip. We have the vertical axis that transverses the center of gravity, and the longitudinal axis that transverses through nose to the tail. So we have the forward thrust from the engines, move the aircraft forward. Also, you can see the mean aerodynamic chord position. 25% of the wind chord is the mean aerodynamic chord, which is the position of the maximum aerodynamic pressure or aerodynamic lift, and it's also the position where the stall begins over the wing. The airflow becomes detached over the wings, so the aircraft starts to stall. It's also the position where the center of gravity of an airliner aircraft is usually positioned. You can shift the center of gravity forward or at this position by moving passengers, cargo, and fuel around the aircraft. So also you can see we have other vectors. We have this times the distance from the center of gravity all the way back to the horizontal tail or the vertical tail is the lever arm or the moment arm that makes the aircraft pitch up or pitch down like this, climb or descend using the horizontal tail component force, or make turns left and make turns right by deflecting the airflow when the aircraft is flying. Also you have moment arms for the ailerons and the spoilers. So it times the distance from the center of gravity all the way back to the horizontal or vertical tail times the surface area of the horizontal or vertical tail or flight control surface times the airflow of the air mass per second times the acceleration of the air gravity, and you have the moment arm or lever arm. Also you can see the wings that produce the lift for flying. So you can see the bottom surface of the wings is more flat, so the airflow of the air mass is moving faster below the wing. No, it's moving slower below the wing. So the air has higher air pressure below the wing, and this creates an aerodynamic lift that pressurizes the aircraft up into the air. So we have positive air pressure below the wing. Also you can see the top surface of the wing is more curved. It has a higher curvature above the wing, so the airflow of the air mass moving much faster above the wing. So we have lower air pressure above the wing, which creates an air suction above the wing, sucks the aircraft wings up into the air. So this is the differential positive and negative pressure above and below the wings of the aircraft that create the aerodynamic lift and forces. So now we'll show you now we'll talk to you about the flight controls and show you a couple of things like the horizontal trim stabilizer, the flaps, and so I will show you now the flaps. Wait a second. So I show you the flaps. We have the speed brakes, the flaps lever. We have the autopilot disconnect switch. This is the horizontal trim stabilizer, which is a kind of flight control. Also the aileron trim position. You can see the horizontal trim of the horizontal tail stabilizer over here moving up and down like this. You can move it. You can see the needle moving up or moving down manually. Also this is the parking brake. This is horizontal trim stabilizer manual tab. Also you have the rudder trim over here in the aileron trim. And the position, you can also see that in the display layer. Also if we have a failure of the horizontal trim stabilizer, we have the cutout switch here. If we have a failure of the CODR hydraulic system, which affects the autopilot and the auto throttle over here. Electric trim, if we have a failure of this two hydraulic system, we can disconnect this and we have only the manual if we use the cutout, so we won't have an auto trim. Also this is the fuel cutout switches for the left and right engine, the fire extinguishers left and right engine, the weather and terrain reflections radar, radio communication panel here, and the transponder. So you can change the setting for the transponder, also test if it works, so you can see other aircraft. And this generates a warning here for traffic, as you can see, and in the display. So now we'll show you, I will talk to you now about the flight controls of the aircraft. So you flight control using the side switch over here. So So also I'm using this side stick over here for controlling the flight controls of the Boeing 777-300 in this simulation. So I will start now with this flight control, the side stick I'm using, the Lszh Extreme 3D. So then I'm gonna make the engine start demonstration and show you the overhead panel after that. So you can see here I'm having my Lszh Extreme 3D. So you can see I can pitch up and pitch down, and I'm using this. So you can see the display over there in the computer. I can climb or descend, pitch up and pitch down. Also bang roll left and bang roll right. Also use the rudder pedals simultaneously, left and right turn. So you can see the other side is interconnected over there. So I have full flight controls for the Boeing 777-300 the airliner when I'm going into flight. So you can see both sides are interconnected. You can see the side stick deflection is proportional to the yoke deflection of the control column and the control wheel for the elements of the spoilers and the elevator. So also have the engines here, the thrust levers like this, forward and aft, idle thrust or maximum takeoff like this. So now I'm gonna show you the outside view. Also I have the horizontal trim stabilizer over here. I can leave neutral. So I'm gonna show you now the outside view of the same component of flight. So I'm gonna show you the flight controls here. And you can see how I use the side stick to control the flight controls in flight. So you can see I have full side stick deflection proportional to the yoke and the flight control surface. So I can climb, I can descend, I can bang roll left and bang roll right. Also the rudder pedals left and right. So I have a full control. Also in the neutral, horizontal trim stabilizer. So this is all for the flight control. Now I'm going inside, show you the overhead panel and the display, the lower display, the systems, electrical, hydraulic, flight controls, audio, data and reference unit, fuel system, electronic control for the engines, and bleed air and pressure vibrations. I'm going inside. We have a few more minutes left for this. We have about 12 minutes for starting the aircraft engines. So we have the overhead panel again over here. You can see inside the cockpit a beautiful view. So we can set here the flap settings for takeoff 15 degrees. We have again the stabilizer trim, the parking brakes, up and down, the speed brakes. So also the thrust levers, you will see the thrust levers moving like this. Also the displays over here and the autopilot, very beautiful view. So you can see a more clear view of the autopilot over here and the functions, also the flaps position, the landing gear. So we come on the overhead panel. You can see here we have the hydraulic fluid disconnect for maintenance in the ground. We have the circuit breakers for maintenance, also the ADIRU, the air dynamics reference unit that controls and displays the airspeed, the terrain position, GPS position, the gyroscopic acceleration and deceleration, the rate of climb, descent, the barometric altitude, magnetic north pole and true north pole, always using this small switch, the ABU over here. Also thrust asymmetry compensator, flight control computers on and off. The APU, the auxiliary power unit, moved on. The battery, primary and APU, and the left and the right engine, IDG, the grid drive generators, the backup generators. So these are the electrical system controls. We have the window heat, the passenger oxygen, the ram air turbine, the hydraulic. We can turn off all the hydraulic pumps. You will see what happens. We're gonna have some failures. So we're gonna see some fault over here, and some failures. Alternate flaps over here. Hydraulic pressure demand C1, C2, and L, and also we lose the stabilizer. Horizontal stabilizer. No, maybe no autopilot. No auto land. So we go over here, we reset again, we lose many system, back to the on. The hydraulic system, left engine, right engine, and air pressurized C1 and C2 electrical. So this is the main panel, electrical, hydraulic, flight controls, air data and reference unit. This is the lighting system and the windshield wipers of the aircraft. The fire control for the cargo and the APU, the electronic engine control normal or alternate, the auto start on and off over here. So you can see the auto start for the engine. We have the fuel jettison over here. We can dump some fuel like this. Select the nozzles to dump fuel in the tank. The crossfeed for the fuel tanks, the center tanks is empty. We have the yellow press. The left wing, right wing is on, and the forward and the aft pumps. The wing and engine are the eyes over here, on or auto. The cabin pressurization auto right now. Of the aircraft cabin pressurization auto or manual, we use the outflow valves, climb or descend, open, and select the landing altitude or close. So we select back to the auto. We have the left engine, right engine, bleeder, pressurizer for wing and engine at the eyes, hydraulic fluid C1 and C2, air conditioning and ventilation, and cabin pressurization. Also the APU at the backup, so we can turn off all this, see what happens if we close this system. We're gonna lose many systems here, it's gonna fail. So you'll see bleed isolation, bleeder isolation, also the hydraulic fluid and the duct pressure. We have no common pressurization, hydraulic pressure demands C1 and C2. So we reset back to the on, to the auto or on, either one. So this is the main systems for the overhead panel. Now we go in this side, CDU and ECL. So we have the synoptics, the engines, the status. You can see the APU is running, the hydraulic fluid, the oxygen level, the checklist, the normal before start, what we need to do, the items to complete, no normal menu, communications, navigation, synoptics. We have the doors of the Boeing 777 closed and the cabin can be pressurized, the landing gear, the pressure inside the tires and the temperature of the brakes, electrical left engine, right engine, the APU is running, and the backup generator. So you can see the main batteries here, the APU and the battery voltage 27 volts, and the APU, and also the charger discharge the average. So you can see the generator over here is connected. We have the flight management computer over here. So this is the hydraulic. You can see the hydraulic fluid, where it goes, the system that uses it, 3 cabin PSI, left engine, right engine, and also the center C1 and C2, which are pressurized, the shut-off valve, and the electric fluid, and also the rotor fluid quality of the hydraulics, left wing, right wing, and the center body wing tank. You can see the center is empty with yellow crosses. Left wing 51,000, right wing 51,000, total 102.2 thousand. Cross feed valves on, forward the naft pumps on. You can see the flow of the fuel, low and high pressure left and right engine, and also the APU is fed from the left wing using the left direct current motor. Also you can see the minimum fuel temperature here at which below the fuel will freeze if you fly high altitudes. So also the air system, left engine, right engine, APU, hydraulic system, pressurization C1 and C2, air conditioning and ventilation, cabin pressurization. You can see if I move the thrust levers forward, also the duct pressure, there is more pressurizer from the engine. Some of the thrust levers back. And the last item for this section, we have the flight controls. You can see I can move the flight controls, the wings, the horizontal, the vertical, and the spoilers. So you can see everything is working here accordingly like this in this section. So I can move control wheel and control column. So you can see everything is working. So this is all for this section. I'm going back to the engines. Also we need some lighting maybe. So we have to turn off both engines like this. You will see both engines off, and the overhead panel is reset. Some electrical, some lighting is off because no engine power. You can see the N1 and the A2. The engine auto starts left and engine auto start right. Engine shut down. We have right now, and we have no fuel flow, and the A2 is decreasing also. So we're gonna have dual turbines, the right wing and the left wing, in a restart mode like this. So we have above 20%. All the conditions are okay, so we can move the fuel control on. We can let the fuel flow from the low and high pressure fuel valve because we have the pressure from the APU, the auxiliary power unit, which pressurizes already the left and the right and the left wing. You can see both turbofans now moving. We are okay, so we can proceed in the takeoff phase now. Both turbines, engine start complete. One last step over here. We have the menu, FMC. So we have the index, the ident, position, initialize, set the reference position, GPS position, inertial reference. For this airport, zero fuel weight, gross weight, reserves fuel, cruising altitude 35,300 feet, 100% cost index, minimum fuel temperature, and the center of gravity for flight. This airport, departure, destination, copy paste, the runway for takeoff, departure again, while we have it inverted. So we have Lszh. We're gonna use the route 1, Transnegro 1 Alpha, Transamity. We can use 2 routes and arrival. So we cancel the discontinuity, activate and execute, and we have the rest 15 degrees of flap, center of gravity 36% with this takeoff speed for this weight and this runway length. So we're ready for takeoff. Everything is set. So here we are, just having maybe, I don't know, maybe like 18 more minutes. So disarm the parking brakes, advance the thrust levers, idle thrust. So we have like 18 more minutes, and use also the tiller over here for steering. So proceed in the runway, which is open. We take the runway clearance and the takeoff clearance from the air traffic control. So we stop here and continue. Align here with the rudder pedals. So we align with the runway, center line, LNAV on, the autopilot is ready. Also the indications here, we use Lszh scan. So you see now the terrain and the flight path. Flaps is set, takeoff trim set. We use the takeoff ground thrust, and we have the view here where we are located and where we're going. So we're gonna use this view, a nicer closer view like this, and we can go disarm the parking brakes and go. So we have like use maximum takeoff thrust and align with the rudder pedals. Now we have higher airspeed. Also use this a little bit. So 100 knots. V1, we rotate. So we start the rotation. As you can see, so we have a positive rate of climb. We track the landing gear. You can see the indications as we climb. Pitch trim a little bit down, not exceed the pitch ladder. So this is the indications. Now we are 2,200, 2,400 feet above the ground level, but 4,000 feet above the sea level. Climb with 8,000 feet per minute. You can see the airspeed here, 200 knots, the ground speed, the flaps limit, and also the stall speed 145. The warning is stalling at about 130 knots, 135. You can see the waypoints we have to follow, the navigation. So now it's time to start making the turn. You can see we keep climbing here, the positive needle. You can see how close we are in the stall speed margin with the flap margin as we keep climbing. A nicer view from outside, and we have like 14 more minutes for this video to end. So I hope you like. Now we're gonna see a nicer view from outside. Again, you see the airport. We have the beautiful Switzerland, the Swiss Alps over here, and the galaxy view of the star sign. So this is our spacecraft for tonight, the Boeing 777-300ER, crossing the galaxy over this Switzerland view and beautiful lakes. So maybe a closer over here. of the Boeing 777 300ER. So how we like, we fly with about 500 kilometers an hour or 250 meters per second as we cross the sky like this over the Switzerland, the Swiss Alps. So this is how we climb. We have also the first waypoint over here. So we cross the first waypoint down here and then make a turn. So we have, you can see the Zui is 1.4 nautical miles, 1.3. We are very close right now. We are overflying it. We are 15,000 feet, keep climbing. So we have like 11 more maybe minutes left as we keep climbing. You have this beautiful view. You have the Germany, the Bayern Munich in front of you, and the France on this side, the Switzerland here, and the Italy behind. So we keep climbing. We have also this beautiful lake over here. $18,000 feet. And we need some more airspeed like this. Airspeed component. So we're gonna use maximum takeoff thrust now. $18,000 feet. 19,000 feet. You can see we climb quite fast. We almost reached the first waypoint we need to reach. 32,400 feet. We have the Germany, the Bayern Munich, the France on this side, and we overflying the lake. Now we're gonna have the chemtrails over here on the contrails, so you can see we have this beautiful view. We can level off for a while and then make the turn. So we overflying the lake. We have the Germany here, the Bayern Munich in front of us, and the France on this side, and the lake below. So you can see the frozen vapors, the chemtrails, and the contrails. So you have also, this is our spacecraft for tonight, the Boeing 777-300ER, this beautiful airplane, this beautiful airliner, jet airline. So we go back to the airport now. We cross the first waypoint, the second, we keep climbing. We're gonna cruise level now over here over the lake. We cruise level. We're gonna cruise level with we're gonna retract the flaps with Mach 0.78 or 980 kilometers an hour airspeed. 35,800 feet or 7,000 meters above the sea level. 7,075. So we have the Germany here again, Bayern Munich. Hope you like this view of the Boeing 777 and the frozen vapors. So this is the galactic view of the Boeing 777. We're flying with 300 meters per second or 980 kilometers, almost 1,000 kilometers an hour, almost a Mach speed. So beautiful view, and now going back to the airport. So we need also so we have 8 minutes left for this flight. Perhaps we can connect the autopilot as for display and set the altitude now. Also the approach reference, we'll select the last waypoint here. And also the approach airspeed. Like this. So we're gonna level off and we're gonna have to start descent in a couple of minutes. So now we cruise with the autopilot of the Boeing 777 300 VR, Mach 0.777, 335 knots, 35,300 feet. So this is our spacecraft at night from the frozen top over here of the galaxy view, as you can see. The Switzerland, the German, and the France. So now we're gonna start descending. We're gonna select here from the autopilot and lower altitude. And decrease the airspeed. So here we descend. We have about 7 minutes left for this descent and approach Flught. So we keep having the chemtrails like this, flying this altitude 34,000 feet. You can see the radar. Also we can set the vertical speed. And set also the speed brakes like this for a fast descent. And we have like maybe decrease the airspeed even further. $31,000 feet. Keep descending. Take manual control now, landing gear down, and select here to pilot disconnect. We have like 3 more minutes left for this simulation trend. So we need that to accelerate a few things. Keep descending. We have the river in front of us. And we cross the cloud. We have the terrain scan here and the runway in front of us. We have maybe like a couple more minutes for this video to end. Simulation video limited. So here we go, descending. So we have the Lszh localizer like this. You can see we are very close to the glide slope here, 1900 feet above the ground level. The horizontal localizer and the glide slope. We use manual thrust, also manual glide controls. You can see the ground below. The airspeed is above the stall speed as it should. So we use manual glide control, increase the rate of descent, and align with the center line with the runway. We use the ailerons again, we level off a bit. Also the rudder pedals and the ailerons for align with the center line. Here we are, level off, 50, 30, 10, idle thrust, touchdown, parking brakes and reverse thrust. So we have the full reverse thrust and slowing down the aircraft. As you can see, we made a very beautiful landing. So you can see the nose wheel here is perfectly safe. There is no breakage of the tires or the metal parts, no buckling of the metals or the tire of the Boeing 777 of the nose wheel, or the landing gear behind, the left and the right landing gear. All the tires and all the metal parts are safe. Also the aircraft, you can see in this view, this side view, is standing up the way it should be in its wheel, without any breakages or damage, not like some other pilots are doing with their airplane. So that was a very smooth landing. So thank you very much one more time for joining me. This Flught of viewers from Hatsios, the British American Palestine, the break to 1700 years. See you next time. Bye bye.